brought to you by Sublette BOCES and the Sublette County Conservation District. If you, weren't able to make it today, or you know somebody else, I guess, that would have liked to have made it today, we will be recording this version of the webinar, and it'll be available on the SECD website as well as the BOCES website shortly if you'd like to share that with people or view again. We would love to hear from you at the end of this recording. So if you have any questions, write them down throughout, and then Gabe will do his best to answer them at the end. We can all unmute then and ask some questions. And so I'd like to introduce today's presenter. His name is Gabe Fancher. After graduating from Colorado State University with a degree in soil and crop science in 2014, he began working as a soil scientist with the NRCS in Pinedale, during which time he mapped nearly 100,000 acres in Sublette County and Lincoln counties. In 2018, he returned to the family cow-calf operation in Wheatland, Wyoming, briefly stopping on ranches in Oregon and Sheridan, Wyoming on his way there. This fall, he enthusiastically came back to Pinedale, ready to assist SCCD. You are likely to see him out trail running in the evenings or climbing and skiing on the weekends with his big white Pyrenees in tow. So with that, I'll welcome Gabe. He's going to actually come over to my computer. So I'm going to share the screen now and we'll get going on the presentation. Can everybody see that okay?
All right, well, thanks, Jess. Yeah, started here in September. I'm kind of the office grunt. I work in a little bit in every department, the range department, the water department, and even a little bit with the wildlife. So without further ado, happy St. Patty's Day. Let me tell you a little bit about salts in Sublette County. I chose this topic because salts are omnipresent. They're around us everywhere, in our landscapes, in our houses. And there's so many terms surrounding salts that it's easy to get completely confuddled. I know I still do. So just to familiarize us all and get us thinking about salts, there's salts in our kitchen, table salt, sodium chloride, Arm & Hammer, sodium bicarbonate, salts on our roads and walks. I know we're still using them, trying to melt the sidewalk here in front of the district. Calcium chloride and mag chloride on the road. I know it helps, but it's sure a mess to drive on. And you see salts every day in the schools and the gym for Bart Simpson drawing on the chalkboard, calcium carbonate, or chalking up the barbells with magnesium carbonate. But being a natural resource manager, I think I'm most interested in salts in our soils and waters. Here's a little picture of the soap holes over outside of Daniel. Here's a brief roadmap of everything that I'm going to talk about today. First, I'm going to explain what a salt is, then how we measure salts, where do salts come from, then bring us all up to speed with some terminology surrounding salts. Then look at salts in the soil, because I'm a soil scientist and I have to go there. Types of salt-affected soils in Sublette, and then bring it home. How do you know you have a salt problem? How can you identify salts and know if they're a problem to productivity or your infrastructure, what have you? And then we'll look at a couple management strategies if you do have a problem. So, getting right into it. What is a salt? Well, we have to go all the way back to freshman year chemistry and look at the periodic table of elements and know that salts are a combination of elements. Salts come together to form compounds. These compounds are electrically neutral and they're in a defined atomic arrangement. The salts that we care about most are the ones that are biologically important, keeping us healthy in terms of minerals and vitamins, and also the ones that are just most abundant in the environment, the ones that weather out of the rocks and control the landscape's functions. So I'm going to start off with a real simple salt that we all know of, table salt. We're going to look at two atoms, a sodium atom and a chlorine atom, and they're going to come together and share an electron. One gains an electron, one loses an electron, or electrons. But the result is two atoms that are charged. A positively charged atom is a cation, and a negatively charged atom is an anion. And I'll speak a little bit more about this here. Salts consist of an anion and a cation. An anion is going to be negatively charged, and a cation is going to be positively charged. There's lots of different kinds, but the takeaway is that one's positive and one's a negative charge. So that's what a salt is. Next, how do we measure salts? Yeah, a couple ways. And they're not with measuring spoons. Sorry to mislead you. Electrical conductivity is the first way. And we use electrical conductivity because water by itself is a real poor conductor of electricity. But the more salt you add, the more those ions we just talked about dissolve in water, and you have positive and negatively charged atoms in the water, and those charged atoms are going to carry the current. So, just a reminder, more salt equals more ions equals more conductivity. Looking over here at this table, if you were to turn your tap on right now, the EC of your water would be in the 50 to 800 range. The snow melting in your yard might be in the 2 to 50 range. And then if you were lucky enough to go to Cancun for spring break, that salt water would be 55,000. And the unit here is typically decisiemens per centimeter. All right, the second way we measure salts in either water or in soils is by taking this metric called TDS, total dissolved solids. We've all, or a lot of us pet owners, have forgot to fill up the dog bowl before, and you come back a day or two later and you see a white ring where the water used to be. Well, all those solids are left after the water evaporates. If we were to scrape up all those solids and measure them and put that as a weight per amount of water that was there, that's how we'd get TDS. Units for TDS are typically parts per million. TDS is a great way to measure salts, but it's not specific. Anything that's left over when the water evaporates gets counted. So this can include pesticides, herbicides, whatever else fits through a 2-micron filter. Yeah, mineral water is going to be a little higher in the 300 to 500 range, and our nice mountain water up here by the mountains close to Pinedale is going to be in that 100 range. Moving on down the line, we've covered what is a salt, how we measure it. Now we're going to look at where it comes from. Well, it comes from rocks. And rocks weather both chemically and physically. Water will do both those. Here in Sublette, we have mostly igneous and sedimentary rocks. I included metamorphic rocks just because We got a couple, and it was a good excuse to show a picture of Devil's Tower. I'm going to speak mostly about these sedimentary rocks because they are the majority of Sublette County's exposed geology, and that's where most of our salts are coming from. They're easily weatherable, and we see them everywhere. The main sedimentary formation, geologic formation here in the county, it's called the Wasatch Formation. It's made up of several different members, but they're all pretty darn similar. This formation includes includes sandstones, siltstones, mudstones, some conglomerate layers, even a few layers of coal. Yeah, they're easy to see. Just think about driving down the roads, looking up at the mesa, or looking at the Wyoming front. You've seen it everywhere. So I know that was quick, but salts come from the rocks. The rocks that weather most easily are the sedimentary geologies exposed in Sublette. Next in the list is salt terminology. This is just going to catch us all up to speed and maybe clear up some of the jargon that gets thrown around when we're talking to land managers and out on the landscape. Saline. So there's a lot on this slide, but don't let it intimidate you. It's really pretty simple. Saline just means there's a lot of salt. Not caring about what type of salt, just there's a lot of it. Sodic, on the other hand, refers to a lot of sodium in relationship to calcium and magnesium. Sodic soils have their own special group because sodium is so powerful in terms of its effect on soil structure and its effect on plant health. And then here in the West, you always hear alkaline and alkalinity and alkali. They're not all the same, but they're often grouped together. And so I just want to straighten up a few things. Alkali generally refers to mineral salts of alkali metals, calcium, magnesium, potassium, and sodium. Alkaline refers to the pH. pHs that are above 7 are deemed alkaline. And then if you ever hear around the terms white alkali and black alkali, when organic matter interacts with alkaline minerals, it turns black, and it's often this grayish, greasy color on top of the soil. So that's black alkali. All right, clear as mud. That was salt terminology. Now we're going to move right on ahead into salts and how salts affect soils. We touched on this. Rocks, weather into soil. And soil is important because it filters our water and it gives us this amazing medium to grow plants in. Now, soil is not dirt. Dirt's under your fingernails. Soil's the ground, the electric skin of Earth, as some people call it. And soil is made up of 3 different particle sizes: sand, silt, and clay. Any combination of those is going to lead to a loam of some kind. I'm going to focus on clay because clay, while being the smallest particle, is the most chemically active and really important to its physical and chemical characteristic. So this is a great slide. What does clay look like? Well, clay is made up of little sheets, and the sheets can form all different kinds of arrangements, but they usually come in these stacks, like you can see in the picture, zoomed way in on an electron microscope. All right, so those little layers that I showed you in the previous slide, Well, they're made up of an aluminum sheet in purple and a silica sheet in green. I'm going to move right along, but keep this in mind because the atoms in the silica and the aluminum sheet will interact with the ions from salts. So just to remind you, there's our periodic table of elements, and there's those sheets, and those little charged ions are going to interact with the surface of those clay layers, either on its edges or on its face. When they do, interesting things happen. The two phenomena that we as soil scientists often pay attention to are dispersion and flocculation. Now, flocculation is just a fancy way of saying that when those ions meet up with the clay particles, they're going to glom onto it and hold it really tight. And you're going to have little aggregates of clay sheets. And on the opposite side of things, when an ion latches onto a water molecule and then it interacts with the clay, it can disperse it. Clays typically have a negative charge, and water has a slight negative charge on the oxygen side of things, or on the hydrogen side. But the important thing here is that clays are either going to group together and spread apart. When they spread apart, the soil is sealed off and you have really low infiltration rates. Low infiltrations means low soil water and more erosion. When clay particles group together and form aggregates, we have more porosity in the soil and better infiltration. So, and then, not to belabor the point, but a sodium ion is most likely going to cause dispersion, while this calcium ion, the Ca2+, is going to cause flocculation. All right, so when salts dissolve in water and then the water comes into the soil, that water is going to move in the soil and deposit salts somewhere along its movement. That deposition can either occur on the surface and we'll get a nice soil crust like we see in this picture here. Sorry, I forgot my cursor's going. Or the soil is going to deposit in the profile. We got some pictures of different salts here. The salt deposited on the far left picture is a calcareous horizon. We find plenty of those in Sublette County. And then salt crusts like Bonneville down in Utah. Those are in very, very arid environments. Then we have a gypsic horizon, also found in Sublette, and then a natric horizon. Natric, it's going to have a lot of sodium in it, and it's going to have these characteristic little caps on top of the columns. Those are called kneecaps in soils lingo. So there's a lot of different factors that affect soil structure, but salts are definitely one of them, along with parent material, organic matter, and particle size. Parent material, lots of forming factors. But salts can either form a granular structure or a platy structure, or contribute to a prismatic or a blocky structure as well. All right, so just to recap thus far, we know what salts are, we know how we measure them, where they come from, some terms behind them, and then the outsized effect they have in soil. Now, I want to talk a little bit more about those soils, and I'll be brief about this, but there's three major kinds of salt-affected soil. There's saline soil, sodic soil, and saline sodic soil. They have the following characteristics. We look at sodium absorption ratio, which we just want to see how much sodium is present compared to the other salts present. Electrical conductivity, how much salt is present as a total measurement. pH, is it acidic or basic? Exchangeable sodium percentage, sorry about the typo. ESP, we want to know, fine, is there a lot of sodium present in the soil? But how much sodium is going to come off of that clay and interact and play in the party with water and plants? And then here in Wyoming, we have lots of calcium carbonate in the soil that can vary. And here's a physical property that's usually associated with these following soil types. Saline soils might have normal porosity, but remember, sodium tends to seal off the surface and you'll have poor porosity. All those pores are full of little clay platelets. Instead of being grouped together, they clogged up the whole works. And so saline soil can be either, depending on the proportions of sodium and other salts. Now I broke each of those types into its own individual slide because there's a management difference in each of them and a remediation difference to each. So saline soils, they're gonna accumulate a lot of soluble salts, which means the best way to remediate those soils is leaching them. Leaching is when we irrigate in excess of the plant need and we try to flush those soils out of the root profile. Sodic soils, remember these are the ones with a lot of sodium. They're poorly drained and they tend to crust. You can still grow crops, but you have to pour the water to them continuously. If you're going to try to treat a sodic soil, you need to remove the sodium from the profile, which means you need to add other ions to take the place of the sodium on the clay surface. And once you do that, you need to get that sodium out of there, again, leaching. So oftentimes around here, you'll see lime being added to the soil. While that lowers the pH, which also helps with nutrient uptake and specific ion toxicities in plants, it's also solubilizing calcium, which is going to knock the little sodium ions off the clays. Saline sodic soil, you got both problems. You got salts and you got sodium, so you're really in trouble. Again, remove the sodium and then leach. But I want to highlight this last bullet point I'm making here. Do not attempt to leach first because dispersion of soil aggregates will be amplified. Unless you have something to take the place of sodium on the clay, you're just going to exacerbate the problem. So, moving on. Here's some maps specific to Sublette County. As you can see in the previous slide, we look at electrical conductivities above 4 as being salt affected. Here's Sublette County, and there's a lot of soils with ECs above 4. They tend to be more out in the sedimentary geologies and less so in the mountains. And because salts dissolve in water, water flows downhill, they're going to be in these waterways specifically, as well as sodium. Here's a map of sodic soils in Sublette County, or I shouldn't say sodic soils. They're soils with SARs greater than 13. Also in waterways and often weathering off of the sedimentary geologies. Okay. We're nearing the end. Now I want to speak about knowing how you can tell if you have a salt problem. There's a couple different ways. 4 of them I've highlighted. Get out your shovel and dig a soils pit. Remember those pictures of the soil profile? You can see salt on the surface, you can see it in lower horizons, but digging a soil pit's a great way to find salt. Salt's typically not going to be a problem if it's down below the root zone of the plants in concern. Second, send it to a lab. We here at the district can recommend several labs that you can send in your soil or your irrigation water for salinity tests or sodicity tests. It's fairly inexpensive and will definitely tell you what you need to know. Third is look for salt tolerant and salt adapted species. Mother Nature will tell you if you have salts. I'll go into that here further. And then lastly, I wanted to make a shout out to the Sage and Snow Garden Club. The NRCS has teamed up with them in the past to do some real rudimentary soils analysis. So that can be a good starting spot. All right, management strategies. And I'm combining this with knowing if you have salts. Walk out on the range, walk out in your pastures, and see if you have any of these species. We got greasewood, we got saltbrush, we got winter fat, we got a couple different grasses. These all can be really great forage. They'll grow in these otherwise harsh environments. They can accumulate too much salt to the point that they become toxic. And they often are indicators of what salt. They can let you know not just that salt's there, but what salt. Here for winter fat loves calcium carbonate. So that's one strategy. Second strategy is irrigation. These 2 pictures are from the same pasture. One's been irrigated and the salts have been leached. It's really productive. And the other one is not irrigated and it's not very productive. So irrigation. Here I have 3 different pictures, different types of irrigation. We do a lot of flood irrigation here in Sublette. The home gardeners might do some drip, which is great because it doesn't use as much water, but some real sodicity issues can occur. And then I wanted to include a picture of a center pivot down in Farson. Farson's got some real salty soils, and those center pivots have leached a lot of salts out of the profile and allowed them to grow some amazing crops. But those salts definitely traveled somewhere, and that became an issue. So, my second bullet point before I move on, it's not just how much water, it's the quality of the water and then the timing of the water. A little tiny plant's going to be super sensitive to salts. Water's going to latch onto that salt, and it's going to latch on so tightly that the roots aren't going to be able to pull it away from the soil. So if you have a little tiny plant, be sure it's getting plenty of water. And then there's all different kinds of strategies about plant spacing, spacing your drip tape, spacing your furrows, yada yada. And then for this center pivot sprinkler down here, salts can affect your plant in the roots, but they can also affect the leaves as well. A sprinkler with really salty water is going to burn up your leaves. So monitor salts in your water. So you have salty soil, you have salty water, and there's just not much you can do about it. Well, here are some expensive, but still can be marginally effective strategies. Bring in topsoil, add topsoil. Salts can be really hard to get out of the soil. If your soil's just not going to work for you, bring new soil in that's not salt affected. Also, add organic amendments. This can be manure or compost, even mulch. Wood mulch on top reduces the evaporation, which keeps the salts low, not on the surface. Organic matter also has the unique ability to bind with salts. Better to have it on there than the soil. I know a lot of people are going to see this picture full of this wheelbarrow full of horse turds and go, that's a major source of salt. And yeah, it can be. You should test for it. But that organic matter can also bind a lot of those salts. The next strategy would be salt-tolerant forage species. Ryegrass, basin wild rye, and then even some fescues are going to have fairly good tolerance to salt, salty soils and salty waters, especially basin wild rye. For the gardener who wants to grow salt-tolerant plants, I've broken it into 3 categories: woody fruits and trees, ornamental grasses and ground covers, herbaceous fruits, veggies, and flowers. Now, I know a lot of us that garden here in Sublette County have gone to raised beds and probably brought in soil that wasn't terribly salt affected. But if you're planting right in your backyard, right in the soil that's there, asparagus, beets, carnations, and chrysanthemums are good choices. Looking here at ground covers, it's really tough to get a nice lawn in Sublette County, and salt is super tough on turf grass. So I might suggest native grasses like blue grama and buffalo grass. And then I have Russian olive in here. I know that's pretty controversial. So juniper and pine and hackberry are also really good woody species that do well in salt affected environments. Pardon me. Okay, well, that was it. And I know I rushed through it, but here's the quick recap. Learned what a salt was. Started with the periodic table. Looked at elements combining to form compounds. Salty compounds are made up of ions. Then we measured salts with TDS and EC. Then we looked at where salts come from. That Wasatch geology in Sublette County is big. We looked at terminology. I hope I straightened out some things like alkalinity, sodicity, and salinity. Then we looked at salts in the soil. There were several different kinds of salt-affected soil, each one with a different management strategy. That was saline, saline-sodic, and sodic soils. Then ways to identify if your property is affected by salts. And then a couple management strategies. Everything from do nothing about it and enjoy the salt-tolerant species that are there. There's some great forage value there. To plant new species, to bring in topsoil, to irrigate and flush the salts out. And yeah, I just hope everybody got something out of that. Feel free to call us at the district or the NRCS. We're both great resources and happy to help. That's the end. Happy St. Patty's Day. And I'm ready for questions and comments if there are any.
Yeah, so feel free to unmute, and you can even turn your camera on so we can see you, and we can ask some questions for Gabe. Does anybody have any questions? Can't let them off that easy.
Yes, you can. Sure. Oh man.
All right, well, I guess if no one has any questions, if you enjoyed this Conservation Conversations presentation, please check out our website, Facebook page of the BOCES website for more information on the remaining 2 that we have in this series. The next presentation will take place on April 21st, where Sherry Meeks will cover secrets of the sagebrush sea. So you can mark your calendars, and we would love to see you at that one. Thanks for coming, everyone.